Another topic and skill that you need for all of science is understanding and creating plots and graphs. We've talked to people in the biology department and they tell us that this is one of the things they really want us to be training you on in Physics 131 and 132. So we'll be focusing them not only in class but also in the laboratory section. You need to not only be able to read and understand data from plots and graphs, since that's how all scientists make and display their data, you also need to be able to create plots from data. And in this movie, we'll show you some basic skills on how to do that. So there are a bunch of different types of plots, but some of the most common types of plots that you'll see in papers for science and also in the newspaper are scatter plots and probability distributions or histograms. In a scatter plot, you literally have two variables. One is the dependent variable. In this case, I'm showing you temperature in degrees Kelvin. And the other is the dependent variable, which is plotted on the y-axis, the coefficient of thermal expansion. In a probability distribution, the x-axis is the variable that you're interested in, and the y-axis is the frequency or the probability of that particular variable coming up. In this case, it's intensity of an image, and then the y-axis shows you the frequency. As you know, the x-axis is where we plot the independent variable, and the y-axis is where we plot the dependent variable, as I just said. You want to be able to understand fits to data as well as just the data itself and what it's saying, because many times in science we're interested in fitting a model to our raw data, and we want to be able to understand if the model works or not through fitting an equation to the data. So for example, in this first scatter plot that I'm showing you, which is actually from a Millikan oil drop experiment where you can measure the charge of the oil drops and the multiples of electron charge, you can see that it has a linear dependence. We can then fit a linear equation to it of the form y equals mx plus b. As you probably know from high school math, m is the slope, which is the change in y over the change in x. This type of concept will come out again and again in Physics 131, and the idea of a slope should be second nature to you. We can also find the y-intercept, which is b in the equation, and that's the location of where the line goes through the y-axis. In this case, the y-intercept goes through at 0, but that's not necessarily the case for all examples. Another scatter plot shown here is showing you radioactive decay. So this is a substance that is decaying over time, and it has the form of an exponential decay of the form y is equal to a times e to the minus x over c plus b. In this case, the variables of the fit are a, the amplitude, which is shown by these curly brackets here. It doesn't necessarily always go to 0. It's the difference between the height and then the final asymptote or limit of the plot or of the decay. That long time limit or that long asymptote at large x or dependent variable is b in this case. And then c is and that you can see at the end of the plot with these arrows. And then c is the decay constant for this exponential decay. It is the characteristic decay constant for this plot, which is falling off. And that's shown here in with this box, where this box is showing you the location. If x equals c, then you have decayed by 1 over e, which is the height here. In this case, it's around 70 counts. And then the time of that exact location, which is around 240 seconds, that time is the characteristic decay time for this data set. As we talked about earlier, when you're looking at data or thinking about problems, you really need to also consider the units. And so let's talk a little bit about the units for this first plot. The slope has units of x over y. Whatever the units of x are and whatever the units of y are, it's the ratio of the two. So for instance, in this case, the units are charge per q. The units of the y-intercept are always equal to the units of y. So in this case, it's charge. That makes sense because if you plug these units into the equation, then we know that b must have the same units of y, but m must have the units of y over x. In the same way, the exponential decay fit variables also have units. The amplitude has units of y, and the long time limit also has units of y. And that makes sense as well because they must have the same units of y. We know that exponentials have no units, and what is inside the exponential exponent also cannot have units. So that means that x and c must have the same units. So that implies that c must have the units of x, the dependent variable. Let's think about our data graphically and do an example. The example says you have a 20 centimeter candle that burns down to 2 centimeters every hour. I want you to plot the height of the candle as a function of time. And then you'll use the plot to determine what time the candle is 2 centimeters in height. So we're going to use our goal system again that we just discussed. And we'll start by gathering information. We know that this candle gets shorter over time, so we have an idea of the direction that our plot should go over time. The candle's not going to be getting taller, it's going to be getting shorter. The initial length is 20 centimeters, which is given in the problem. The speed of loss of the candle is 2 centimeters per hour. And finally, we want to know at what time the candle will be only 2 centimeters. Next step is organizing our approach. Let's draw a picture. For the candle, it's kind of easy to think about. We know that at time equals 0, so at the beginning, our candle is 20 centimeters. 1 hour later, it should have lost 2 centimeters, so it should be 18 centimeters. 1 hour later, it should have lost 2 more centimeters, so it should be 16 centimeters, and so on. This is almost our plot. The only reason why this is a picture and not a plot is because we don't have axes for a plot. And so we can almost take this and create our plot. We can also pull out information and make it more of a shorthand, quantitative way of saying things. We can assign our variables. So let's assign the letter L to be the length in centimeters, the lowercase letter t to be the time in hours, and m will be the rate of candle loss in centimeters per hour. We know that we should be putting then L is going to be the dependent variable, so it should be on the y-axis. Y should be the dependent variable. X should be the independent variable, so it should be on the x-axis. And this rate of candle loss is actually going to be the slope of our plot. We should say that since it doesn't say that the rate that the candle burns down changes, we expect that this will have a constant rate of candle loss, and so m will be a constant number. So let's take this information and try to put it into a plot. So we have these two axes, the x-axis and the y-axis. First thing to do is to label these, and this is still part of analyzing the problem. Oh, this is now part of analyzing the problem. So we have the candle length as the y-axis, the time in hours on the x-axis. The next thing we need to do are make reasonable tick marks on the side. These tick marks should be evenly spaced, and they should cover the entire range of both the dependent and independent variables. So for instance, on the y-axis, it should go from 0 to 20 centimeters. And on the x-axis, it should go from 0 to 10 hours, although you might not know how long it should go, so you could maybe have extra there. Now we're going to plot the height of the candle over time. And again, we just had that very nice picture, and we know that every hour it's going to lose 2 centimeters, and it starts at time equals 0 at 20 centimeters. 1 hour later, it's lost 2 centimeters. 1 hour later, 2 centimeters, and so on, and so on. Until at 10 hours, it's actually 0 length. We've burned up the whole candle. The slope should be 2 centimeters per hour. And we could actually fit a line to this slope, y equals mx plus b. In this case, m is the rate of candle loss, and b will be 20, because that's the y-intercept at t equals 0. It should be noted that this equation is not just an equation. It actually conveys all the information that was given to us in the example. So finally, we need to make sure, now that we have our plot, we need to make sure that we're answering all the questions. So again, we look back at the example questions, and it says, use the plot to determine what time the candle is 2 centimeters in height. So we want to know when that happens. We can easily read that off the plot. It occurs when t equals 9 hours. So finally, we should think back and learn from our efforts. In this case, we could solve this problem in a completely different way, maybe in a more physicsy or quantitative way than plotting. We could actually use the fit line, y equals mx plus b, to find t when y equals 2 centimeters. We know that y will be 2 centimeters. We know m is negative 2 centimeters per hour. We know b is 20 centimeters as the intercept, as I described earlier. And x is going to be t hours, which is our unknown. We don't know how many hours it will be. I want to stop here for a second and point out the fact that our slope is negative. You should be able to figure that out from the fact that the candle is getting smaller. So that means that our slope must be negative 2 centimeters per hour. This is another example of how looking at the problem and understanding it will give us more information. We can rearrange the equation y equals mx plus b to solve for x, or which is equivalent to t in hours. So we get y minus b all divided by m will equal x. We can plug in y, b, and m to find that we get 9 hours, the same as we did before. By solving this question in a different way, we can check our answer, but in addition, we can double check that we understand the physics behind this process.